One can have a lot of fun with electrostatics. Let's take this perspex rod, rub it with a synthetic skin, and in the process we rip off charges. Let's say we rip off electrons, so now the cloth is negatively charged, the perspex rod is positively charged. If we then take some particles, very tiny styrofoam particles, we can collect them easily, and in the process we also collect the rod. This electrostatic attraction between particles of different charges, positively and negatively charged particles, was first discovered in the 18th century, and it was Alessandro Volta in 1775 who discovered and invented this device, which is called the Electrophorus. Here we've got a perspex sheet, which we again charge up using a skin or a cloth. Let's say we're ripping off electrons, and then we place it in contact with a conductor. Here we've got aluminium, and we touch it, lift it, and present it to someone else, and there is a discharge. What a surprise! Let's do this again. Oh, there's another discharge, and so on. It seems like an unlimited supply of electricity. Look, discharge after discharge. Maybe you can hear this. Did you hear that? I'll do it once more. There it was. If you've been observant, you notice that in between the discharges I made contact with my finger, which is relatively moist, and that's in fact the reason why it charges again. Oh, if I don't do that, there is no discharge. I have to make contact here to the aluminium bit, to the conductor, not to the dielectric, not to the perspex, to the conductor. And there is another discharge. You can see a bit better what happens if we take this version of the Electrophorus, which is a little bit more sophisticated because it's got this indicator here. And I make contact again with my body, and let's see what happens. Aha! The two aluminium foils repel each other because they're both equally charged, and as you know, equal charges repel each other. Opposite charges attract, and if I now make contact again and get the spark, the discharge has occurred, and you can see that because the aluminium leaves are not repelling each other again. And if I make just contact with the dielectric, nothing happens. But if I make contact and contact with me, which you might have guessed by now is Earth, I'm Earth, I'm making contact with Earth, we have charge on the Electrophorus and a discharge, and so on. So this Electrophorus may be considered one of the oldest electrical instruments, as I said, invented by Alessandro Volta, and it may give the impression of an infinite supply of charge. However, that is not the case. What happens is here that electromechanically, by rubbing, the charges are removed from the Electrophorus, from this perspex sheet, that's the dielectric, and since the charges that are left, let's say positive charges that are left now, since they're immobile because this is a dielectric, they can't move away, they stay there. So the dielectric stays positively charged forever, until of course through the moisture of air it gradually leaks charge to air in the environment. But if we now place on this charged perspex the conductor, we influence the mobile electrons in the conductor, and they are repelled. So this causes a charge separation. And if we now connect to Earth by connecting with our body, with a finger or with a toe, whatever you prefer, then we're drawing charges from Earth onto the metal, which compensate the charge separation. So now we have overcharged the conductor, and that overcharge remains if we separate. As you see now, we have this overcharge, and then we lift the Electrophorus, and we have this excess charge which then can be discharged back to ground. And I might switch off the light so that we can see if we can illuminate a fluorescent light bulb in the process. I might take the other small electrophorus for this and give this perspex sheet another rub to really charge it up, and then have charge up this smaller electrophorus, take a fluorescent light bulb, connect to one end of it, and let's see what happens. Did you see that? I'll show you again. Yep. We can create light from static electricity. Wonderful. One can also nicely demonstrate Coulomb's law this way, because we have, I've got these two styrofoam balls, very light, but they are coated with carbon paint, which is conductive. And if I make contact here, then charge up, you can see that we have a demonstration of Coulomb's law. Yeah, you can see that the two equally charged particles repel each other. So there's a force acting between them which repels each other. So this is the Coulomb force. I've just discharged them, but I can charge them again carefully, like this. And here they come again. Unfortunately, they touch my body in the process, so we have to do it once more to have a convincing result. Here it is. I think now you can see it really nicely. They separated in space, and that separation is due to the Coulomb repulsion between the two.